The universe holds plenty of secrets, but none of them are more disturbing than the silent inconsistencies hidden in the very mathematics that describes it. These aren't minor errors. They're blaring contradictions in how we perceive the universe. With decades of research, precision instruments, and leading-edge equipment, you'd imagine the numbers would finally add up. But they don't. And that's a problem. We're talking about things like the rate at which the universe expands, a foundational value in cosmology. Despite precision instruments and highly controlled observations, the results just don't agree. They contradict each other in ways too big to ignore. This isn't background noise. It's the universe quietly suggesting we've misunderstood something deep and fundamental. And now the James Webb Space Telescope has poured fuel on the fire. Its findings are beginning to rock the foundations of cosmological theory, including notions previously considered sacred, such as Einstein's own equations. Some researchers are now coming to the conclusion that dark matter and dark energy don't begin to cover it. Perhaps there is something more, something hidden, remodeling the laws of physics. So what's actually happening out there? Are we on the cusp of changing the way we perceive the entire universe? Let's get in. When the James Webb Space Telescope soared into space on Christmas Day 2021 aboard an Ariane 5 rocket, it wasn't the beginning of just another science mission. It was the beginning of a revolution. 2 decades in the making and supported by an international alliance, Webb wasn't another tool, it was a leap into a new era of astronomy. After its journey of almost 1.5 million kilometers to its destination, the Sun-Earth Lagrange Point 2, JWST started working in July 2022. The telescope, with its gigantic 6.5-meter gold-coated mirror, was designed to observe what no previous telescope could. It doesn't observe visible light like Hubble. It observes in the infrared, showing us ancient objects whose light has traveled over 13 billion years to arrive here. And what did it see? It revolutionized everything. In just its first few months, Webb brought back images and information so revolutionary that some researchers started talking about astronomy in terms of 2 periods, pre-Webb and post-Webb. One such researcher, Dr. Andrei Kutso at the Institute for Theoretical Astrophysics, has gone far enough to say the data could require a complete overhaul of standard cosmology. Why? Because the telescope was observing galaxies that shouldn't be there. Within weeks of being operational, JWST began picking up enormous, luminous galaxies at redshifts greater than 10, that is, when the universe was just a few hundred million years old. Our earlier models said that galaxies this large and luminous could not have assembled so rapidly. But there they were, illuminating Webb's detectors like cosmic lighthouses from a past that cannot be explained. The lambda cold dark matter model, the gold standard for understanding the large-scale structure of the universe, started to totter under the weight of this new data. If the first galaxies were making stars at 10 times the rate we predicted, then the assumptions embedded in our models, dark matter clustering, gas cooling, star ignition, all need to be retested. And the surprises didn't end there. By November 2022, JWST focused on exoplanets, and it hit gold once more. For the first time in history, it found carbon dioxide in the atmosphere of an exoplanet called WASP-39b, a gas giant 700 light-years from Earth. This was not a whisper or a suggestion. It was a solid, definite detection. And it led to something much greater. In the months that followed, Webb revealed water vapor, sulfur dioxide, and even evidence of chemical reactions, photochemical smog, in extraterrestrial atmospheres. It revealed to us just how rich and diverse these far-off worlds might be. Exoplanets were no longer mere floating rocks and gas. They were dynamic, chemically active worlds. These discoveries also compelled planetary researchers to question their models as well. How such planets develop, migrate, and evolve under the control of stars now appears much more complicated than ever imagined. And by the end of 2023, JWST already explored more than a dozen exoplanets, from huge gas giants to smaller Neptune-sized worlds. It then became even more ambitious. Early in 2024, Webb analyzed TRAPPIST-1c, one of 7 Earth-sized planets that orbit a small, cool star. What it discovered was dramatic. TRAPPIST-1c does not possess a dense, carbon dioxide-rich atmosphere, which alters the way we evaluate its possible habitability. The contribution of a star's radiation to stripping a planet's atmosphere is now under close examination. By 2025, Webb had another first. It watched a rare eclipse occur on GJ 1214b, a super-Earth 48 light-years from Earth. That enabled scientists to make direct measurements of the planet's thermal radiation and spot a misty atmosphere full of complex molecules, even possibly prebiotic hydrocarbons. That's not science fiction. That's one step closer to finding life. But JWST isn't just revolutionizing the way we're seeing planets, it's revolutionizing the way we're seeing stars. Its infrared senses enable it to peer deeply into the dust clouds that shroud newly formed stars. It's taken breathtaking photos of the pillars of creation, the Tarantula Nebula and others, unveiling the tumultuous beauty of star birth in exquisite detail. These photos revealed accretion disks, jet streams, and early formation patterns we could never have examined before. The stellar evolution models, the way stars are born, the way they live, the way they die, are being rewritten. Dr. Kutso and others have said that these nurseries are much more complicated and messy than anyone had anticipated. They don't move in neat, predictable ways. They turn and knot like galactic knots, defying old textbook drawings. And this is only the start. Within a little more than 1 year, JWST has executed more than 1,500 scientific programs and returns almost 60 gigabytes of unprocessed data each day. It's detected shockwaves from galaxy crashes and followed elements forged in distant supernovae. It's triggered a wholesale shakeup throughout astrophysics, and nobody's sugarcoating it. For many in the scientific community, the question isn't whether JWST has changed our understanding of space. It's how deep that change will go, and whether we're even ready to comprehend what it's showing us. Consider galaxies, for instance. In 2023, scientists at JWST examined more than 30,000 galaxies from the universe's earliest days, some dating back as far as 500 million years since the Big Bang. What they observed did not fit our expectations whatsoever. These galaxies weren't slow to mature. They weren't crude or primitive. They were dense, enormous, symmetrical. Some even possessed disks and bulges, structures we had believed took billions of years to develop. These galaxies shouldn't have been in our models. And yet there they were. More mysterious was their pattern. How these galaxies were dispersed across the sky didn't conform to the expansion rate we've determined from cosmic microwave background or supernova observations. Those methods are how we've quantified the universe's expansion for decades. If they don't match, one of them must be incorrect. Or worse, we could be misinterpreting the very fabric of space. Additional research in 2024 with JWST's NIRCam and NIRSpec tools verified these discrepancies. Another 20,000 galaxies were tested. Same result. The redshift readings, how much their light had been stretched out as the universe expanded, didn't match our expectations. One of the galaxies had an inferred stellar mass of more than 100 billion suns. And they were observed at redshifts greater than 10, i.e., they were only 500 million years old when the Big Bang occurred. That doesn't add up. Either galaxies evolved much quicker than we imagined, or our knowledge of redshift, a foundation of contemporary astronomy, is incorrect. This is where things get weird. Certain physicists are now questioning whether space itself acts differently than we've thought. Perhaps cosmic expansion isn't uniform. Perhaps space doesn't expand like we believe it does. Perhaps the entire system needs to be overhauled. And just when you think it can't possibly get stranger, step forward, the Big Wheel Galaxy. JWST caught sight of this behemoth, a disk galaxy swirling with light that has taken more than 12 billion years to reach us. Created when the universe was only 15% as old as it is today, the Big Wheel contradicts everything we believed about early galaxies. It's enormous, more than 150,000 light-years wide. It rotates like the Milky Way. It's structured, organized, stable. Theory says that galaxies that young in the universe would have been disorganized, small, chaotic, unstable. But this one? It's a polished product. Its very existence forces cosmologists to question when, and how, large galaxies came to be. Did they evolve slowly? Or did they appear almost overnight in a burst of rapid formation? We don't know yet. But we're starting to realize that our old answers aren't good enough anymore. The Big Wheel Galaxy's mass is a cosmic paradox. It is supposed to be the kind of massive galaxies that take billions of years to evolve. They develop slowly through the gradual union of tiny proto-galaxies. But this one? It appears to have skipped ahead of the cosmic standards. It's not only huge, it contains more than 500 billion solar masses of stars alone. That's many times more than models currently forecast for such an early point in the universe. It's like someone hit the fast forward on galaxy evolution and skipped all the in-between stages. Something isn't adding up. JWST's high-resolution spectroscopy has verified its size, its age, and its rotational curve. This galaxy is not only huge, it's tidy. It's rotating with a stable disk, which totally refutes the long-standing assumption that early galaxies were chaotic whirlwinds. We had anticipated starbursts and haphazard clumps, not ordered, well-formed spirals. So what's going on here? The big wheel isn't an oddball, it's a full-blown challenge to cosmology itself. If something like this can happen so early on, perhaps our whole model for how galaxies evolve and develop is wrong. It's not longer about one bizarre galaxy, it's about what this means. The stakes are enormous. If the lambda cold dark matter model cannot explain this, then we may be missing something more fundamental. Perhaps dark matter responded differently in the early universe. Perhaps some unforeseen cooling mechanism permitted matter to collapse more rapidly than we knew was possible. Some scientists are even challenging our measuring systems. Might our understanding of light, distance, and time in the deep universe be wrong? Might there be things we have yet to understand that are distorting our findings? These are questions now at the forefront. As of 2025, the big wheel stands alone. It's one of the largest, most mature galaxies ever seen from that era. It shouldn't exist, but it does. And its existence tells us that we've only just scratched the surface of what the early universe was really like. But it's not just the big wheel. That would be easy to dismiss as a fluke. The real issue? There are more like it. JWST has now discovered an entire population of enormous, well-developed galaxies at 500 to 700 million years after the Big Bang. Not one or two, dozens. And these are not fuzzy blobs. These are mature, organized, and complete. They rival the Milky Way in size and mass. They exhibit signs of rotation. They possess dense stellar populations. They appear to have been around for a long time, but they haven't. They shouldn't even be here yet, according to our current knowledge. Not just surprising though, it's a crisis. A full-blown cosmological reckoning. Because if there were galaxies like this so early, that means our timeline for how the universe matured is way off. And if we blew that, what else are we missing? Deep field surveys such as Sirius and JADES have uncovered these galaxies lying right before our eyes. Their prevalence implies that this is not a fluke. This is a trend. An indication that something is amiss with our models. They were designed to begin small and gradually expand. But these expanded quickly and they expanded considerably. In February 2023, Evo Lab and Erica Nelson-led researchers published results from the JADES survey that stunned the community. They discovered 6 galaxy candidates created between 500 to 700 million years after the Big Bang, with masses of 10 to 100 billion solar masses. That's Milky Way scale. That early. These galaxies weren't merely large. They were structured. They had structure. And the processes it took to form them, gravity, star formation, collapse of matter, simply shouldn't have had a chance to get to work. The universe, that youth, was supposed to still be staggering from the Big Bang. Hot, turbulent, unstable. Rather, it appears to have already been constructing cities in the sky. Theorists are flailing. Because the numbers don't lie. The math tells us these galaxies shouldn't exist. And if they do exist, that means we're missing something big. Perhaps dark matter was clumping more quickly than we realized. Perhaps gravity was behaving differently. Perhaps unknown forces were at work. Some are calling for adjustments to theory of inflation. Others propose supermassive black holes that existed earlier and contributed to quicker star formation. There are even rumors of as yet unknown physical laws that may have existed only in the early universe. It's an open-ended frontier. And while mentioning unknowns, one can't keep quiet about dark energy. Initially, dark energy was brought in to account for the fact that the universe is expanding at a faster rate than anticipated. For decades, it was regarded as a constant, a consistent, unchanging force embedded in the fabric of space. But now, that notion is being challenged. Observations from JWST indicate dark energy may not be constant after all. It may be evolving, changing, getting stronger or weaker over time. And that makes everything different. If true, it upends one of the fundamental pillars of contemporary cosmology. For more than 20 years, the notion of constant dark energy has shaped how we comprehend the universe's expansion. But now, there is evidence that it could be variable and change depending on where and when you measure it. One of the largest warning signs is from a conflict called the Hubble tension. That's the discrepancy between the rate of expansion derived from local observations, such as type Ia supernovae, and the rate extracted from early universe information, such as the cosmic microwave background. They simply don't match. Now JWST enters the scene, bringing high-resolution data from a crucial time period, redshifts 3 to 10. That's a cosmic window we've never really been able to study closely before. And it's in this window that something strange is happening. Early indications are that the rate of expansion at this point isn't what we thought. It could mean that dark energy's power has varied. It's not constant, it's responsive. And if that's the case, we're looking down the barrel of a complete cosmological overhaul. That would imply dark energy is not simply a background. It's active. It behaves. And its behavior might be based on something we don't yet know. Some new field, some new particle, even a new law of physics. It's the sort of revelation that makes physicists rethink the fundamental architecture of space and time. Einstein's equations held for a century. But if dark energy is changing, we might need more than relativity. We might need to step into quantum field theory. Or even string theory. Some say that dark energy might be a result of interactions between gravity and the quantum vacuum. Others believe it's something even more unusual. How did we arrive at this point? It all traces back to 1998. That's when two groups of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, made a finding that turned everything on its head. They were studying faraway Type Ia supernovae, stellar explosions so uniform in brightness that they are used to gauge distances throughout the universe. But what they discovered surprised them. These supernovae weren't just distant, they were fainter than they ought to have been. That meant the expansion of the universe wasn't decelerating. It was accelerating. To account for this, scientists came up with a new force, dark energy. Some sort of unknown that spread space apart. And with that, everything was different. The notion of a big crunch, where the universe would collapse under its own gravity, was junked in favor of something much more bizarre. A future where space merely continues to expand. Where galaxies move away forever. Where the universe grows cold and desolate. Einstein had originally inserted a cosmological constant into his equations to maintain a static universe. Then he declared it his greatest blunder. But today that constant was revived, and more potent than ever. By today's standards, dark energy constitutes 68% of it all. Dark matter gets another 27%. And what we can see, stars, planets, us, only 5%. Consider it. Everything we've ever touched or known is merely a fraction of the entire universe. The rest is imperceptible, enigmatic, potent. Since 1998, the pursuit of dark energy has accelerated. Telescopes such as Planck and the Dark Energy Survey missions were dispatched to pursue solutions. And JWST is continuing where they had left off, illuminating a force that we still can't explain. The 2011 Nobel Prize in Physics was awarded to scientists who had detected accelerating expansion. But even they acknowledge, we still don't know what dark energy is. Is it a constant, as Einstein once suggested? Or is it alive, evolving, interacting with the cosmos in ways we've never seen before? JWST's early findings are pointing toward the latter. If confirmed, it would change everything. Physics, cosmology, the fate of the universe itself. It's like we've opened a door that leads into a hallway of more doors. Behind each one, a new question, a new mystery. We've come a long way, but we might still be at the beginning. The debate over how fast the universe is accelerating its expansion has intensified in recent years. At the center of this disagreement is something known as the Hubble tension. It's the continued disagreement between two ways to calculate the rate of expansion of the universe, and they just won't agree. When scientists measure the expansion of nearby galaxies with Cepheid variable stars and Type Ia supernovae, they find an expansion rate of around 73.3 kilometers per second per megaparsec. But when they observe the early universe with the cosmic microwave background, that figure falls to 67.4. These figures should be the same. But they aren't. For years, researchers prayed for better measurements to make the problem disappear. But the chasm instead remained large. It's become increasingly difficult to dismiss as mere error or inconsistency. And now new information is making the issue impossible to avoid. Into this already fiery debate came DESI, the Dark Energy Spectroscopic Instrument. Its purpose is to chart the redshifts of more than 30 million galaxies and quasars. The plan is to monitor how the expansion of the universe shifted over time. But early on, DESI discovered something strange. The findings suggested dark energy, the unseen force propelling expansion, may not be so steady. Initially, most scientists wrote off the measurements as noise or provisional. Perhaps the local arrangement of galaxies was skunking the data. But then something shifted. Webb's observations came in. With its precision imaging and deep reach into the early universe, JWST confirmed some of DESI's hints. Webb found expansion anomalies at various epochs that current models couldn't explain. It wasn't just a single moment in time, it stretched across billions of years of cosmic history. What started as a disagreement became a crisis. Webb's data matched the scale and structure of DESI's anomalies but took them further. Back to galaxies just 300 or 400 million years after the Big Bang. These galaxies shouldn't be showing up with those properties, yet they do. The news is evident. Dark energy, the name given to it, may not be a consistent, one-force phenomenon. It may evolve with time. If so, our current paradigm, the lambda cold dark matter model, could be incomplete or perhaps just plain wrong. Einstein's equations and the idea of a cosmological constant have shaped our view of the cosmos for a century. But if dark energy evolves, those equations might no longer describe the universe as accurately as we thought. More scientists are now seriously considering the possibility that cosmic expansion operates under more complicated rules than we have thought. Perhaps it's time to change our models, reinterpret our assumptions, and seek out fresh solutions. This overlap between DESI and JWST has transformed a formerly specialized scholarly problem into a defining struggle in physics. It's not merely about learning how quickly the universe is expanding, it's about rewriting the physics rulebook for how the universe operates. One of Einstein's most iconic concepts was the cosmological constant. He first proposed it to keep the universe static, then withdrew it. But after the 1998 discovery of accelerating expansion, it roared back to life. The notion of a repulsive force embedded within space itself became the basis for the explanation of dark energy. It worked, at least for a period. But Webb's high-resolution data is putting cracks in that foundation. If dark energy changes over time, then Einstein's constant isn't so constant after all. And if that's the case, the very equations we've been using to model cosmic expansion might need serious revision. General relativity might still work where gravity is intense, near stars, black holes, or planets. But on the cosmic level? Possibly not. Possibly we need something other than that. Something greater. Something that includes dynamic expansion and changing energy fields. This introduces the possibility of new and occasionally bizarre concepts. Altered gravity. Emergent spacetime. Ideas where the actual architecture of space may emerge from quantum phenomena, not as a background. Certain physicists are looking back to earlier ideas such as quintessence, where dark energy is a time-varying field. Others are looking into the possibility that dark energy has something to do with quantum fields, or even hidden dimensions. Sounds like science fiction. But at present it might be our best way out. And this is only the beginning. Webb has barely scratched the surface. As it keeps up its mission, and as additional instruments come in on the hunt, the entire discipline of cosmology may experience a revolution. The Roman Space Telescope is coming next. So named after NASA's first chief of astronomy Nancy Grace Roman, it's due to launch sometime in the mid-2020s. And it's offering a different kind of strength to the game. As Webb zooms in with breathtaking detail, Roman will appear wide. Its task is to scour enormous sections of the sky, detecting broad patterns and structures that show how the universe acts at its largest scales. Among Roman's greatest ambitions? Map dark energy. Monitor it. Chart it. Determine whether it really does evolve over time, or if something else is afoot. Roman's infrared imaging over wide fields will enable astronomers to map galaxy clusters, investigate how galaxies form, and explore the physics of Type Ia supernovae. These supernovae are cosmic yardsticks that allow us to measure distances of billions of light-years. Roman will also support exoplanet science. It won't have the high-resolution power of Webb, but its capability to survey vast swaths of space means it will be able to detect patterns in entire populations of exoplanets. It'll tell us where worlds are made, how they develop, and where we should look for evidence of life. Together, Roman and Webb will make an unbeatable team. One looks deep, the other looks wide. And between them, they'll paint a fuller picture of the universe than we've ever had before. But even with all this data, we're still early in the game. Webb's observations of galaxies beyond redshifts of 10 have disturbed the world's wisdom of early galaxial buildup. These were made earlier and in a smaller fraction of the available time. They're formed. Mature. Mature looking to look like it isn't to belong in any earlier universe other than the very beginning 500 million years ago. Our previous models predicted early galaxies would be disorganized, tiny, and slow to mature. Webb disagrees. These galaxies are structured and luminous. They shouldn't exist, but they do. Another place JWST is rewriting the book? Reionization. This is when the first stars and galaxies ionized the surrounding gas of hydrogen into plasma. Scientists still aren't certain how rapidly that occurred or what caused it. But data from Webb indicates it could have occurred far more rapidly than thought. That implies early galaxies were accomplishing more than we credited them for. They might have influenced the evolution of the universe in radical ways, something our models don't yet pick up. Webb is also making us reconsider black holes. It has picked up hints of supermassive black holes that appear far too large for their age. Some are billions of times more massive than our Sun, and they were in existence a few 100 million years after the Big Bang. How did they become so massive so quickly? Did they originate from gigantic stars that collapsed directly into black holes? Did they begin smaller and expand rapidly through rapid accretion? Or is there some other, unknown process involved? These black holes can also affect how galaxies assemble around them. Or perhaps it's the reverse. We don't know yet. But these are some of the most thrilling questions in all of astrophysics. And of course there's dark matter. We don't know what it is yet. But Webb has already revealed to us how it molds the universe. By observing gravitational lensing, how light bends around heavy objects, Webb can chart the unseen scaffolding of the universe. What's odd is that dark matter might not be as passive as we've assumed. The way it clumps, travels, and interacts with normal matter indicates it might be more active than anticipated. Some scientists ask whether there are exotic forms of dark matter we haven't yet found. Or perhaps dark matter interacts weakly with something other than gravity. The data is preliminary, but the questions are accumulating. Looking forward, it's obvious that the future of space telescopes is no longer about a single mission. It's about collaboration. Webb, Roman, Euclid, DESI, they'll all add pieces to a bigger puzzle. Each telescope has its own strengths, and together they'll assist us in revealing truths we couldn't access on our own. We've learned so much, but in so many ways we're still just starting out. The future holds more detail, more questions, more discoveries. We're going to discover new galaxies, observe new exoplanets, and perhaps, just perhaps, discover hints of life beyond Earth. What we do know is this: we're living in a golden age of discovery. Our tools are more powerful than they've ever been. Our questions are bolder than they've ever been. And the answers? They're arriving quickly. It's a future that's full of mystery, of possibility, and of the promise that perhaps, just perhaps, we're finally beginning to realize our place within the universe. Well, that's all for now. Thanks for watching. If you liked this video, please like, comment, and subscribe so that you don't miss what's next. And don't skip the video that just appeared on your screen, it'll blow your mind too.